This is section 3.2, Rolle's theorem and the mean value theorem. All right, so the extreme value theorem states that a continuous function on a closed interval a to b has to have both a minimum and a maximum on that interval. Both of these values, however, can occur at the endpoints. They can have an endpoint minimum and an endpoint maximum, for example. Rolle's theorem, named after the French mathematician Michel Rolle, gives conditions that guarantee the existence of an extreme value in the interior of a closed interval. And so he was saying that if you have a continuous function, so again, that continuity idea is really making itself heard again and again here. So we have a continuous function, and I'm just going to draw some random graph, f of x. Let f be a continuous function on the closed interval from a to b, and differentiable on the open interval from open a to open b. If f of a equals f of b, so I'm going to pick two places on this curve where the y values are the same on purpose. So this y value is f of a and f of b. So that's a condition for Rolle's theorem. First condition being you have a continuous function. And the second one is that f is differentiable. On the open interval a to b, and number one I forgot to write, it's continuous on the closed interval from a to b. Okay, and the third condition is that f of a equals f of b. If all of those things are met, those are the conditions for Rolle's theorem. Then, if all three are met, therefore, or then, there is at least one number c. Hold on. Then c exists. So this is another existence theorem. C exists such that f prime of c equals 0. So somewhere, and this c, by the way, has to be between a and b, and that c exists at least once. Can happen multiple times, but at least once there's going to be a place between a and b where you have a horizontal tangent line at c. And in that case, if it's differentiable, it's not going to be at c a place where it's a undefined derivative. It's going to have, since it's differentiable, that means that the guarantee that it'll be 0 has to happen somewhere between a and b. Okay? If you look at a picture like what I've drawn, that kind of makes sense. And at that c, isn't it possible that we would have, therefore, at c a local maximum or a local minimum? In this picture, it's a local minimum at c. So that's what he was trying to get at. Okay? All right, so these three steps are the conditions that have to be met for Rolle's theorem, and this down here is the conclusion that c exists so that f prime of c will be equal to 0. So there'll be at least one horizontal tangent line between them. If you drop the differentiability requirement, it's possible that you'll still have a critical number on the interval from A to B. That would look like maybe this. If it doesn't have to be differentiable, let's say we had something like that. And here's f of A and f of B, whoops, being the same again. So this has the same y value as this does. And at this value of C, we don't have a horizontal tangent line, but we do have a place where it doesn't exist. And there's a relative maximum here. That could certainly happen, but it's not guaranteed. So you have to be very careful that you have the conditions. And it certainly would not make it true that you have a horizontal tangent line. That would not be a conclusion you could draw. So that's something to be aware of, so that you may or may not have a horizontal tangent line if you drop the differentiability component of that three-pronged hypothesis, the conditions that have to be met. All right, so let's do an example. Let's find the two x-intercepts of this function. And we know that x-intercepts occur when y is equal to 0. So solving this polynomial equal to 0, we'll want to find factors of positive 2 that add up to be negative 3. And of course those are negative 1 and negative 2. And so that implies that x is equal to 1 or x is equal to 2. Okay, so those are the x-intercepts. And then we're supposed to show that f prime of x equals 0 at some point between the two x-intercepts. Okay? So since f is differentiable, it's a polynomial, so we know it's differentiable on the entire real line, so it's differentiable any subinterval of that. Well, now we're supposed to show that since we have f of 1, A, and f of 2, B, that are both giving us 0 as an answer, f is a continuous and differentiable function for all real numbers, so we know that we have all three conditions met. F is continuous on the subinterval of all reals 1 to 2. F is differentiable on the open interval from 1 to 2, a subset of all real numbers, and f of 1 equals f of 2. So we have the conditions. So by Rolle's theorem, therefore, because we have those conditions met, we can conclude there must be a value C which is between 1 and 2. There must be that value C, it has to exist, such that f prime of C equals 0. Okay, Rolle's theorem says that has to happen. Now, these two statements, and I said it, but I probably didn't write it very well. These two statements are based on f being a polynomial function. And that's what tells us that we have continuity and differentiability. So if you had to establish whether you had the conditions met, you want to look at the type of function you have and be able to make a claim about its continuity and differentiability on the interval you're looking at. Okay, Then, if they asked us to find C, that's another matter. It's like a part B to the question. Okay, first establish that there is an answer between 1 and 2, such that f prime of C would be 0. Then find that value. Well, to do that, we would need to find f prime of x, which is 2x minus 3. And we'd want to have our conclusion work. We would have to say, well, f prime of C, which is by substitution 2c minus 3, that's supposed to be 0 according to Rolle's theorem. And if we solve for C, we'll get 3 halves. Is 3 halves, in fact, between 1 and 2? Yes, it is. And so that's a good value. Now, what if on a different problem, let's just say, for example, that C was between 5 and 7, and we solved for C and got C is equal to, I said 5 and 7 and I wrote 6. Wow, way to go. Dummy. Getting ahead of myself and making silly written errors. Okay, between 5 and 7, as I said. And our candidates for C were -3 and 6 and 12. Well, which one of those is actually the one that we've been guaranteed will exist? Although the other ones are true too, but which one is guaranteed? It's the one that's between 5 and 7 that we're looking for. So although you may solve for C and get lots of answers, you're only going to keep the 1 or 1s, because it may happen multiple times, the 1 or 1s that fall between A and B. Here are the 5 and 7. So just saying, in case that happens, you'll know that you're looking for all answers between A and B, and any others that you find, you just ignore them for the answer. Okay. And if you look at a graph of this parabola, you'll notice that its vertex is at 3 halves, and 1 and 2 are the x-intercepts. And so you can tell that there's a horizontal tangent line at that vertex. It makes a whole lot of sense. Now, Rolle's theorem is used to prove another theorem. So historically, Rolle's theorem needed to come first to prove the mean value theorem. We're not going to prove the mean value theorem, but I'm saying that if you proved it, you'd have to have Rolle's theorem as a basis. Okay, here's what the mean value theorem is going to say visually. I usually like to talk about things visually first, if there's a visual representation of it, because I think you understand that way better if you can see it to understand it. Okay, so let's say we have a function that is continuous and differentiable on the interval. So 1f is continuous, on closed interval from A to B, and it's differentiable on the open interval A to B. But this time, for the mean value theorem, I'm going to drop the f of A equals f of B idea. So I'm going to make A right here. So that's f of A. I wrote B, darn it. I'm thinking about 2 steps ahead, and so sometimes I write what I'm thinking about that's coming before I should be writing it, so I apologize for that. I'm going to make this x-axis go out a little bit further. Oops. There we go. Okay, so let's have the x-axis go out here. And let's make B right there. Okay, so If you'll recall, one of the things we did early on with trying to figure out how to find the slope of the tangent line was we started with the secant line from A to B. So I'm going to draw that secant in here because it's really important for the mean value theorem. It's tied into that pretty closely. And my claim is that there's going to exist at least one C. And I don't think I wrote at least on the Rolle's theorem, but I should have. So you might want to go back and change your notes to reflect that. There exists at least one value C that is, it's a number between A and B, such that, okay, so again, this is another existence theorem. The existence of C is guaranteed, such that something's going to happen. And before I forget about it, I want to go back up here. Must be at least one value C. There could be multiple ones. I forgot to say that last time, so I want to put that back in there. Such that something happens. Okay, now we're going to get to what that something is. I would like for you to look at this function and think about tangent lines at all kinds of places. And just kind of run from A to B. Just think, maybe hold a pencil and hold it where the tangent line would be as you go from A to B. And what do you notice happens exactly twice, as it turns out, on this graph? There's something special that happens. Well, I'll give it away because I can't show you with my hand that I'm doing that, so you'll just have to sort of go with the flow here. Right here, if I drew that tangent line at that point, and so that's a value of C, and since I know I have two of them, I'm going to call this one C1. And then again, right about here is another place where that happens. And its tangent line looks like this. What's true about the tangent lines that I've drawn? And they're not perfect, but they're actually pretty good. I'm kind of proud of myself. I did a pretty good job here. What can you tell me about those two tangent lines relative to the secant line? Well, I'm hoping you're thinking parallel, because that's the big idea with the mean value theorem, is that those tangent lines are parallel to the secant line. And if the two things are parallel, that means that the slope of one is equal to the slope of the second one. Okay, so I'm going to call that slope of the first line, m sub 1, is equal to slope of the second line, m sub 2. So, and this happened to happen twice, so C1 and C2 is just two instances of this happening. So I want to just basically chronicle one of them. So let's call this line 1, just so everybody knows which line I'm thinking of. And I'm going to call it C, not C sub 2, for the purposes of this. And I'm going to call the secant line line 2. Okay, so the tangent line to the curve at some point will be parallel to the secant line between points A and B on that curve. Okay, so how would we find the slope of the tangent line? Well, the slope of the tangent line is found through the first derivative. And so slope 1 for line 1, that tangent line, that would be that f prime evaluated at a generic C, which in this problem happens to be specifically C sub 2, but I'm just going to call it C for general purposes. That's how you find the slope of the tangent line. It's f prime evaluated at a C value. And what's the slope of the secant line between those 2 points? Well, I forgot to draw in something here that might be helpful. F of B is about right there. That's the y value of the point at B. So isn't that just a basic slope calculation? given 2 points, y sub 2 f of b minus y sub 1 f of a divided by x sub 2, which is b, minus x sub 1, which is a. So the end of that statement, the conclusion of the mean value theorem, given that you have a continuous and differentiable function on a to b, there has to be at least one value c, where c is a number between a and b, such that f prime of c is equal to f of b minus f of a over b minus a. And you need to know this formula, but let me suggest that if you remember, the mean value theorem talks about parallel, and that the tangent line at some point will be parallel to the secant line between 2 points on a curve. If you can remember that part, and you can put together that idea with the slope of the tangent line as the first derivative evaluated at that number c, and that the slope between 2 points is just a regular slope formula, y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1, you will have this formula correct, even if you don't have it memorized per se. If you understand the parallel nature of these things, you can develop this formula correctly if you calculate the slopes correctly. Okay, so this is another theorem you're going to need to know. Rolle's theorem and mean value theorem are both things that you need to have memorized. And by the way, Rolle's theorem, in hindsight, that's actually just kind of interesting, as it turns out. If I have a function, looks like this, in the xy plane, and I pick a couple of values, a and b. If I draw the secant line between these two, and f of a is equal to f of b, we're back to Rolle's theorem, by the way, in this. If f of a and f of b are the same, then what will the slope of that secant line be? Well, f of b minus f of a is going to be 0 divided by some constant b minus a. That'll be 0. And we're saying that there must be tangent lines, according to Rolle's theorem, where f prime of c is 0. Well, isn't that, again, parallel? So Rolle's theorem is actually a special case of the mean value theorem. It just so happens that the secant line, because f of a equals f of b, is a horizontal line, slope 0. That means we're looking for parallel places to that, as far as tangent lines go, where there's a slope of 0. So, in essence, Rolle's theorem can be thought of as a special case of the mean value theorem. And by the way, people who use mean value theorem a lot will abbreviate it MVT for mean value theorem. So that's a good use of that. Alrighty, so let's do a problem. Example 3 is what I've called this, I believe. If f of x is equal to 5 minus 4 divided by x, find all values c, find all values of c in the open interval 1 to 4, such that f prime of c is equal to f of 4 minus f of 1 divided by 4 minus 1. Okay, so the way this is stated, they're making a lot of assumptions for you, but I want to talk about what those assumptions are, because I think it's important that you get this is what's going on. That is the conclusion of the mean value theorem. So what had to have been true before we could even get in there is that f of x had to be continuous and differentiable. So on the subinterval. So what type of function is f? Well, it's a rational function. Because you could get a common denominator and write that as a polynomial over a polynomial. I'm not going to do that, but you could. Wouldn't be that hard to do. And as such, we know it is continuous on its domain and differentiable on its domain. And its domain is, you can't divide by 0, and if x is 0, then that happens. So it's continuous and differentiable from negative infinity to 0 and 0 to infinity. And since 1 to 4 is a subinterval, a subinterval of 0 to infinity, we're good to go, and we have both conditions met. So, and it should be continuous on closed 1 to 4 and differentiable on open 1 to 4, which this isn't a nice clean write-up. This is not even asked for in this problem. I just wanted to say that you could establish the fact that this is actually eligible and that the conclusion they've written for you is actually valid. That has to happen. So, first of all, what I would start with is the derivative of this function. So I'm going to rewrite it, because remember, variables in the denominator are not that good for derivative purposes. So I'm going to write this as x to the negative first. And so the derivative of 5 of 0 minus negative 1 times the 4, because we're bringing the negative 1 down, so that'll be 4x to the reduced by 1 power. So that's 4 over x squared. And so now that we know the derivative, f prime of c, that means we're going to put c in for x. So 4 over c squared has to equal, now f of 4, that's 5 minus 4 divided by 4. 5 minus 1 is 4. Minus f of 1, 4 over 1 is 4. 5 minus 4 is 1. Over 4 minus 1. So 4 over c squared is equal to 1. Taking the reciprocal of both sides, c squared over 4 is equal to 1/4. So c squared is equal to, why did I say 1/4? Wow. Again, I think I'm getting ahead of myself here. The reciprocal of 1 is, of course, just 1, which means that c squared is equal to 4, and c is equal to plus or minus 2. Now, of those values, be careful. We only want the c value that's on our interval. It's not negative 2. It's only positive 2. So make sure your answer doesn't have that negative 2 in it. Okay. One last thing in this section that I want to talk about. A useful alternative form of the mean value theorem is if f is continuous on AB, closed AB, So this is an alternative form of the mean value theorem. So it's just a different form. It's going to have the same hypotheses that f is continuous on AB and differentiable. On open interval a to b. Then C on the interval from a to b exists. Such that, here's the new conclusion. It's the same conclusion, just in a different form. That f of b equals f of a plus b minus a multiplied by f prime of c. So how did they get that? Well, if you start with the conclusion up here, that we have this conclusion right here, and we're writing an alternative form of it. So f prime of c equals f of b minus f of a over b minus a, which the theorem says is the conclusion you can draw. Then, because if b minus a isn't 0, which it better not be anyway, we could multiply both sides of the equation by b minus a. And I think you can see now where I'm going. Then you could solve that equation for f of b if you wanted to by adding f of a to both sides. And there's this alternative form. So it's not like it's anything brand new. It's just a reformulation of the original conclusion, just solving it for f of b. Now, keep in mind that there are a number of functions that are both continuous and differentiable on their domains. We've said that, and this is really important because the mean value theorem and Rolle's theorem don't apply unless these two conditions are met. And that list of functions includes polynomial functions, rational functions, and trig functions, are all differentiable at all points in their domains. So if it's one of those kinds, you know it will meet the conditions. As long as you don't divide by 0, you should be fine. So that will make the conditions of both Rolle's and mean value theorem apply, and you'll be able to draw your conclusions from each one of those theorems. Okay, so that ends this lesson. I will see you in class.